Let's compare a reversible and an irreversible process in an example. So say we have 2 moles of an ideal gas and it's confined in a frictionless piston cylinder system at 5 bar 300 K. The atmosphere, that's going to be the surroundings in this example, is 1 bar 300 K. Clamps are holding the system in equilibrium, but if the clamps are removed, the gas will rapidly expand until the pressure is equal to 1 bar. This step happens so fast that it's adiabatic, but afterwards heat transfer occurs from system to surroundings. And that is a typo. It should say from surroundings to system. Sorry about that. I fixed it from surroundings to system until P2 is equal to 1 bar, T2 is equal to 300 K at the end. Find the work done by the gas and the total amount of heat transferred from the surroundings to the system. So I'm going to pause the video, go ahead and try to draw your process flow diagram. I've already got mine pre-drawn, so I'm just going to copy it in here. And then also see if you can write and simplify the energy balance. By the way, do the mole balance too, or the mass balance, but that one should be pretty easy. Go ahead and pause. So here we go. This is what my diagram looks like. We've got an initial state where we've got a compressed gas, so 5 bar, 2 moles, 300 K. The atmosphere is always 1 bar 300 K, but in the initial state, there are some clamps here that are holding everything at a state of equilibrium. And then once those clamps are removed, boom, instantaneously that piston is going to rise up, expanding the volume of the gas until the pressure is equal to 1 bar. So we've got if we define the system as the gas inside the piston and cylinder, the mole balance is going to be trivial again. So it's closed, so no in or out flows. You can't generate or consume mass because there's no reaction going on. So moles are going to be unchanged, so 2 moles in both cases. But if I want to calculate the work and then the total heat, I'm going to need the energy balance. This is a closed system energy balance, which we didn't quite review in too much detail. So you can derive it from the open system energy balance. You just have to integrate the terms. So anytime there's a d dt, you have to integrate it. And in my MEB class, this is how I wrote the closed system energy balance. So the change in internal energy plus the change in kinetic energy plus change in potential energy is equal to Q plus W. And we've got no change in kinetic energy, no appreciable changes anyway. No change in potential energy. So you may say that the piston is a little bit higher, so therefore it has more potential energy. But that's going to be negligible unless it's a very huge cylinder, and it's not going to be that big. So our closed system energy balance cancels to delta U, and we can write that as moles or mass. So we got to write it on a specific basis. And I'm going to say it's the mass. Even though we have the moles, it's not going to matter anyway, and I'll show you why. Mass is equal to U hat 2 minus U hat 1 is equal to Q plus W. And by the way, both Q and W terms have to stay because the problem hints at the fact that we've got work done by the gas, so that's the W term, and heat transfer from the surroundings to the system. So we've got both. Now, how do we figure out what the change in internal energy is? So there's a couple things that we have to talk about. Number one is that in all the examples from before, we've said that internal energy is a function of temperature and pressure. And that comes from Gibbs phase rule that says for a single component, single phase system, which is what we have here, we have a single gas that is only a gas, there is no liquid. We've got 2 plus 1 minus 1 degrees of freedom is equal to 2. However, the problem statement also specifies that we have an ideal gas. So this is an important corollary of Gibbs phase rule, that ideal gases are an exception for Gibbs phase rule. Our exception for Gibbs phase rule for GPR. And this is because pressure does not affect the properties of an ideal gas. Remember, the important assumption of an ideal gas is that it's under such low pressure that the molecules don't interact anyway. So if that's the basis of your assumption, no matter what the actual pressure is, if you're assuming ideal, you're assuming that the molecules are not going to interact. So regardless of whether or not that is a good assumption, if you take that assumption as fact, you can say that pressure doesn't affect anything. Doesn't affect state properties, we'll say. So therefore, for an ideal gas, U, internal energy, so U hat or U under bar, is equal to a function of temperature only, not pressure. So this says U hat is equal to U hat parentheses a T, which means U is a function of T. So this is the common notation that you'll see in a lot of thermo textbooks. All right, so we've got U as a function of T only, and if we look at the final and initial temperatures, we've got the same initial and final temperature, which is going to mean that the internal energy is going to be the same at the final and initial states. So this is actually going to cancel out because the temperature is the same in the final and initial states. So we're left with Q is equal plus W is equal to 0, or said another way, you can say that minus Q is equal to W. So how do we go about solving this energy balance? We don't have another expression for Q. That's going to have to be what we find later, but we do have another expression for W. So how do we quantify the amount of work that is done by the gas on the system? Remember, there's two types of work, and typically we say in that turbine example that we had shaft work. But in this case, there is no spinning parts or moving parts besides the piston. No useful work is being generated here. The work that we have here is expansion work. So this work is going to arise because of expansion of the system. And we could write that as negative the integral of P dV. So this is looking like something that we can calculate, and we're going to have to integrate this. So we're going to need the limits of integration from the initial to the final state. So let's go ahead and integrate that expression, and then that is going to give us what the work is. And then by the energy balance, we say that negative Q has to be equal to W. So how do we integrate negative P dV? This is a common pitfall that I see of a lot of engineers forget about what this pressure is. Or the inclination here is to say that the pressure in this equation is equal to the pressure inside. And that's not true. The pressure in this equation is the pressure that opposes the motion. So this is going to be like the external pressure that is counteracting the rising of this piston. So in other words, you'd say if we had 10 bar inside and 0 bar outside, there's nothing that's opposing the motion, and then therefore there'd be no work being done because there is no resisting force. So that's how I remember it, as the work done has to be proportional to whatever is counteracting it, not necessarily the amount of work that you have stored up inside. So with that realization for this process, P is always equal to 1 bar. It doesn't change. So for this case, P is always equal to 1 bar. So because it's always equal to 1 bar, it's a constant, and I can pull it out of the integral. So I can say that this is going to be equal to minus P integral of dV from initial to final state. And the integral of nothing is just that variable. So it's equal to minus P, and then V final minus V initial. So VF minus VI. Well, I guess the proper way to say it, not the integral of nothing, it's the integral of a constant, because we pulled the constant out of the integral. So, and no constant of integration either, because we have bounds on our integral. So this is a definite integral, not an indefinite integral. All right, so we're down to work is equal to minus P times V final minus V initial. And in the problem statement, they don't give us what V final and V initial are, but we do have P, N, and T, and we have the crucial assumption that we have an ideal gas. So anytime you have 3 out of those 4 variables, you can simply solve for the other one. So I'm going to solve for V final and V initial. So I'm going to say that work is equal to minus 1 bar times V final is going to be N2RT2. Sorry, I'm mixing up my notation here. If I want to be consistent, I should say this is V2 and this is V1, or I could say final moles, final temperature, but you get the idea. Over P2 minus N1 R T1 over P1. All right, and then all of those variables are given in the problem statement. So if you work out what this number is, I'll let you plug everything in and you can just check your answer. The work done in this case is going to be negative 3,991 joules, which means that the heat transferred, so this W is equal to minus Q, so it's minus a minus, and Q is equal to 3,991 joules, which makes sense because we said that heat was going to be transferred from the surroundings to the system, meaning it's positive, and the system, which is the gas inside, does work on the surroundings, which means it's negative by convention. All right, now, was this a reversible process or an irreversible process? Remember, the criteria for it to be reversible is that it has to be slow, such that there's no large driving forces. We do have no friction, but the criteria that it's slow is definitely not satisfied. The instant we take these clamps off, boom, that piston is going to instantly shoot up. So that means it's an irreversible process. So I'm going to make a note of that. This is for reversible process. Now let's try the same problem, but instead of this is irreversible. Irreversible. Instead of irreversible, let's try a reversible case. So now instead of clamps holding on this piston or holding this piston down such that the gas inside is at high pressure, let's imagine that it's a pile of sand and we're going to get from initial state to final state by removing 1 grain of sand at a time and allowing this piston to come up more slowly. So I've got a process flow diagram for that one as well. So how about this artistry on my part? This is what I envision a pile of sand on top of a piston looking like. I always got a kick out of these whimsical examples, like why would we ever have a pile of sand on top of a piston? Try not to get as caught up in those details as I did. It's going to be an illustration. It's for illustrative purposes only. So for whatever reason, just go with me in saying that we just have a pile of sand on this piston. And as we remove a grain, we're going to say we remove a grain, allow the system to come to equilibrium, remove a grain, allow it to come to equilibrium. So it's kind of as the limit as we go very, very slow up to this final state. So we actually have a ton of other intermediate states as well. This is just an example with a smaller sand pile. So what changes in this case? Definitely not the mole balance. I'm still left with 2 moles initial, 2 moles final. And actually the form of the energy balance is going to be the same as well. So if we have an ideal gas and we still have the same starting temperature, there's going to be no change in internal energy. And we can say that the energy balance is again going to cancel to minus Q is equal to W. And W is again minus the integral of P dV from state 1 to state 2, not the number 1 to the number 2. All right, so what changes? And the change in the reversible case, I'm giving it away that this is going to be reversible, because you can imagine I've got all 4 criteria satisfied. I don't have any large driving forces, so the driving force achieved by moving a grain of sand is going to be negligible or infinitesimally small. It's going to be slow, it's going to be frictionless. I can get back to this original state without any net work. So if I just do the same amount of work to the piston that I get from the system, I'm going to be able to get to the same initial state. But again, the change is this pressure. And remember, this pressure is the pressure that opposes the motion. So don't be tempted to say it's just 1 bar and constant again, because as the diagram shows, the force that opposes the motion is actually this external pressure plus the weight of all this sand that's lying on top of the piston. So the opposing pressure, the opposing force, if you will, is a better way to say it. The opposing force per area is actually a function of how much sand is on the piston at any one time. Unfortunately, that is a little bit harder to calculate. So to get around that problem, what I'm going to do is say that after every grain of sand is removed, I have equilibrium after every grain. So at equilibrium, and I'm going to say I wait for equilibrium to be achieved before I remove the next grain. At equilibrium, all forces are equal. And therefore, if all forces are equal, because nothing's moving, remember, then I'm going to say that the external pressure is going to be equal to the internal pressure. So just a couple of minutes ago, I said that don't mistake this P in this equation as the internal pressure. But in this case, we say that the internal pressure is equal to the external pressure because we have equilibrium states, so many of the intermediate equilibrium states. All right, so how does that change the solving of the problem? Well, instead of P is equal to 1 bar, we've got P that's changing now as a function of time. So as I continue to remove the sand, this pressure inside is going to be slowly dropping from 5 bar to 1 bar. What is the function by which that changes? So we can't just say it changes from 5 to 1. It's definitely not constant, but we use the ideal gas law again, and we express P as a function of V. And in fact, we have to do that because that's the variable that we're integrating over. So I'm going to use the ideal gas law and say that the internal pressure is equal to the moles inside times R times T, and T is constant, so all constants divided by V, and this V is also changing in time. So integral of minus P dV is nRT over V dV. nRT is constant. The integral of 1 over V dV is the ln of V. So it's minus nRT ln of V, and that is going from V1 to V2. And when we have an ln and we subtract them, we can put them over. So this is just calculus. So it's minus nRT ln V2 over V1. And this is equal to our work. All right, we have to apply the same trick and say that V2 can be expressed by the ideal gas law. So we say V2 is nRT, all 2's over P2, and V1 is N1 RT1 over P1. And therefore, if we put them over each other, the n's cancel because those are equal. The r's and the t's also cancel, and I've got P1 over P2, or 5 bar over 1 bar. So I'll leave you to plug in your own variables here again, and I'll just give you what the final answer is. So doing the calculation here for the reversible system, I get work is equal to minus 8,029 joules, which means that Q is the negative of that, positive 8,029 joules. So comparing the answer that you get from the reversible case to the irreversible case, I get more work out of the reversible case, which is consistent with what I've said before, and this is just an illustration of why that happens. If you think about conceptually why the reversible case gives you more work, in the reversible case, the gas inside was doing work not only on the piston system, but it's also lifting up all this extra sand that is lying on top of the cylinder as well. So that's kind of how we get more work out of it. So where does entropy come in? I've said that a reversible process generates no net entropy. So we haven't calculated anything related to entropy. Let's go ahead and do that now. So let's say, what is the entropy for the system, the surroundings, and the universe? So this is an equation that I can write. I can say that delta S for the universe is equal to delta S for the system plus delta S for the surroundings. And I want to calculate each one of those terms. All right, so let's see if we can do this. All right, I'm going to do the irreversible side, or the reversible side on the left and irreversible on the right. And for both of these cases, I'm going to apply the mathematical definition of entropy, which is that ds is equal to dq rev over t. And if I integrate this, I've got S2 minus S1 is equal to q rev over t. All right, for the reversible case, this is the one where we've got sand on top of it. Delta S for the system. So S2 minus S1 of the system. is equal to Q rev, and because it is a reversible system already, I don't have to do anything else to it. I can simply say that Q is equal to Q rev for the reversible system, and I can say that Q is 8,029, and the units of that were joules, divided by T, which is constant at 300 Kelvin. So for the reversible system, my delta S is 26.8 joules per Kelvin. What about for the irreversible case? In the irreversible case, I cannot say that Q is equal to Q rev because we have an irreversible system. So how do we get around that? Well, we have to make use of the fact that entropy is a state property, and we have to imagine a hypothetical path by which you could traverse from initial state to final state, but have it being reversible. And we've already done that. We've already calculated it. Both the reversible and irreversible cases have the same initial and final state. So we're just going to use the Q that we had from the reversible case. So delta S system for irreversible is equal to 8,029 divided by 300K, which is also equal to 26.8. Now at this point, you're probably saying, well, what gives? I thought for a reversible case, we're not going to be generating any net entropy. And we're only considering one side of the equation so far. We've only calculated what the delta S for the system is. We also have to calculate what delta S for the surroundings is. Okay, so let's go ahead and do that. Let's say that delta S for the surroundings in the reversible case. And now, so if you think about like how much energy the system gained, that all has to come from the surroundings. So if we think about the system from the perspective of the surroundings, sorry, this is getting confusing. You have to analyze the surroundings. So now instead of being the surroundings, let's analyze the surroundings as the system. So the Q that is lost by the surroundings is equal to the Q that is gained by the system. Right, so delta S surroundings is going to be negative 8,029 joules. And I don't have to do any kind of tricks because it is a reversible system already, right? So Q rev is equal to Q. So 8,029 joules divided by 300 Kelvin because the surroundings is also at 300 Kelvin. So we know what the answer to that is already. It's negative 26.8 joules per kilogram. If we take the delta S of the universe, it's simply equal to the sum of these. Delta S universe is equal to 0 joules per kilogram. So that makes sense, right? For a reversible process, S dot gen is equal to 0. For the irreversible process, how is it different? For an irreversible process, remember my Q in this case was not 8,029, but rather, where's my answer here? Rather, it was 3,991 joules. So that's the amount of energy that is being added to the system. But if you think about the surroundings from a system point of view, the surroundings aren't changing by very much ever, right? We assume that the surroundings are going to be large enough, the environment is so large that the temperature never changes from 300K. So in that sense, what's happening to the surroundings is indeed reversible because there are no large gradients. Nothing is happening to the surroundings very fast at all. So in this case, delta S for the surroundings is equal to minus the heat that is transferred to the system. So minus 3,991 joules over 300K. And this calculation gives you not 26.8, but minus 13.3 joules per kilogram. And when you add those together, I've got delta S of the universe that is non-zero. It is equal to 13.5 joules per kilogram, which is comforting because remember, we should never get a change in entropy of the universe that is negative. That is theoretically impossible. The universe has to be gaining entropy all the time. So that's the end of this video. Before I move on, I'm going to show you my notes, and I'm just going to scroll slowly through them. So these are going to be my notes from the first and second videos from today. And you can pause this if you'd like in order to copy anything down. I think I explained things in a little bit more detail, so if you missed anything, you can see what I've written.